As useful as it is, the ideal gas law provides no insight as to how pressure and temperature are related to properties of the molecules themselves, such as their masses and speeds. To show how such microscopic properties are related to the pressure and temperature of an ideal gas, this section examines the dynamics of molecular motion and develops what is known as the kinetic theory of gases. The pressure that a gas exerts on the walls of a container is due to the force exerted by the gas molecules when they collide with the walls. We start by combining the notion of collisional forces exerted by a fluid with Newton's second and third laws of motion. These concepts will allow us to obtain an expression for the pressure in terms of microscopic properties. We will then combine this and the ideal gas law to find the average translational kinetic energy of a particle in an ideal gas in terms of the temperature. In the process, we will also develop an equation for the internal energy of a monatomic ideal gas. To get an intuitive feel for the relationship between temperature and pressure, consider a macroscopic container filled with a dilute gas at low temperature. The gas atoms or molecules collide with each other and with the walls of the container and move with different velocities. If we increase the temperature, the gas particles still move with random velocities, but the average speed of the particles increases, thereby increasing the pressure on the container. The atoms or molecules have different speeds. However, it is possible to speak about an average particle speed. At any given instant, some particles have speeds less than, some near, and some greater than the average. For conditions of low gas density, the distribution of speeds within a large collection of molecules at a constant temperature was calculated by the Scottish physicist James Clerk Maxwell. Here we show the Maxwell speed distribution curves for a gas at two different temperatures. When the temperature is 300 K, the maximum in the curve indicates that the most probable speed is about 400 meters per second. At a temperature of 1200 K, the distribution curve shifts to the right, and the most probable speed increases to about 800 meters per second. To give you an idea of how fast these particles are really moving, the speed of sound in air is about 343 meters per second. One very useful type of average speed, known as the root mean square speed and written as VRMS, is also shown. When the temperature of the gas is 300 K, the RMS speed is 484 meters per second, and it increases to 967 meters per second when the temperature rises to 1200 K. The meaning of the RMS speed and the reason why it's so important will be discussed shortly. Let's have a closer look at the collisions between the gas particles and the walls. If a ball is thrown against a wall, it exerts a force on the wall. Gas particles do the same thing, except that their masses are smaller and their speeds are greater. The number of particles is so great that they strike the wall so often that the effect of their individual impacts appears as a continuous force. To calculate the force, consider an ideal gas composed of n identical particles in a cubical container whose sides have a length L. Except for elastic collisions, these particles do not interact. Let's look at one particle of mass m as it strikes the wall perpendicularly and rebounds elastically, and by elastically we mean with no loss of energy. While approaching the wall, the particle has a velocity of plus v and a linear momentum of plus mv. The particle rebounds with a velocity negative v and a momentum negative mv, travels to the left wall, rebounds again, and heads back toward the right. The time t between collisions with the right wall is the round-trip distance 2L divided by the speed of the particle, that is, t equals 2L divided by v. According to Newton's second law of motion, in the form of impulse momentum, the average force exerted on the particle by the wall is given by the change in the particle's momentum per unit time, or the average force equals the final momentum minus the initial momentum divided by the time between successive collisions. This is written as minus mv minus the quantity mv divided by 2L divided by v, which equals negative mv squared divided by L. According to Newton's law of action-reaction, the force applied to the wall by the particle is equal in magnitude to this value, but oppositely directed, meaning the average force is positive mv squared divided by L. The magnitude F of the total force exerted on the right wall is equal to the number of particles that collide with the wall during the time t multiplied by the average force exerted by each particle. Since n particles move randomly in 3 dimensions, 1/3 of them on the average strike the right wall during the time t. Therefore, the total force is F equals N divided by 3 times M times V squared average divided by L, where V squared has been replaced by the average value of the squared speed. The collection of particles possesses a Maxwell distribution of speeds, so an average value for V squared must be used, rather than a value for any individual particle. The square root of this quantity is called the root mean square speed, or, for short, the RMS speed. So V RMS equals the square root of the average of V squared. With this substitution, the total force becomes F equals N divided by 3 times M V RMS squared divided by L. Pressure is force per unit area. So the pressure P acting on a wall of area L squared is P equals F divided by L squared equals N divided by 3 times M V RMS squared divided by L cubed, which is equal to N divided by 3 times M V RMS squared divided by V, where V is the volume of the box. We can rewrite this relation as PV equals 2/3 N times 1/2 M V RMS squared. This equation relates the macroscopic properties of the gas, its pressure and volume, to the microscopic properties of the constituent particles, their mass and speed. Since the term 1/2 M V RMS squared is the average translational kinetic energy, Ke bar, of an individual particle, it follows that PV equals 2/3 N times the average kinetic energy. Recall from the ideal gas law that PV equals NKT. We can therefore write NKT equals 2/3 N times the average kinetic energy. The number of particles N cancels on both sides, and we are left with the average kinetic energy equals 1/2 M V RMS squared, which equals 3/2 KT. This result is significant because it allows us to interpret temperature in terms of the motion of the gas particles. This equation indicates that the Kelvin temperature is directly proportional to the average translational kinetic energy per particle in an ideal gas, no matter what the pressure and the volume are. On the average, the particles have greater kinetic energies when the gas is hotter than when it is cooler. If two ideal gases have the same temperature, the relation 1/2 M V RMS squared equals 3/2 KT indicates that the average kinetic energy of each kind of gas particle is the same. In general, however, the RMS speeds of the different particles are not the same because the masses may be different. Air, for example, is primarily a mixture of nitrogen, N2, with a molecular mass of 28.0 atomic units, and oxygen, O2, with a molecular mass of 32.0 atomic units. If we assume that each behaves like an ideal gas and apply the equation, we find the RMS speeds of nitrogen and oxygen at room temperature at 293 K are 511 meters per second and 478 meters per second respectively. Again, as a comparison, the speed of sound in air at the same temperature is 343 meters per second. The internal energy of a substance is the sum of the various kinds of energy that the atoms or molecules of a substance possesses. A monatomic ideal gas is composed of single atoms. These atoms are assumed to be so small that the mass is concentrated at a point, with the result that the moment of inertia, I, about the center of mass, is negligible. Thus, the rotational kinetic energy, I omega squared, is also negligible. As a counterexample, for instance, a diatomic molecule can have rotational kinetic energy, and this must be taken into account in the derivations. Back to the monatomic gas, vibrational kinetic and potential energies are absent here because the atoms are not connected by chemical bonds and, except for elastic collisions, do not interact. As a result, the internal energy, U, is the total translational kinetic energy of the N atoms that constitute the gas, or U equals N times 1/2 M V RMS squared. Since 1/2 M V RMS squared equals 3/2 KT, the internal kinetic energy can be written in terms of the Kelvin temperature as U equals 3/2 NKT. With K equal to R divided by NA, and N over NA equaling the number of moles N, we have for the internal energy U of an ideal gas, U equals 3/2 NKT, which equals 3/2 nRT. Thus, the internal energy depends on the number of moles and the Kelvin temperature of the gas. In fact, it can be shown that the internal energy is proportional to the Kelvin temperature for any type of ideal gas, being it monatomic or diatomic, etc. In summary, the average kinetic energy of a particle in an ideal gas is given by 1/2 m/v RMS squared, which equals 3/2 kT. The internal energy U of an ideal gas is related to the temperature through U equals 3/2 nKT, which equals 3/2 nRT.